Hello everybody, my name is Hunter Ream and I will be talking about Generating Functionology by Herbert Wilf. In particular, we're going to be talking about section 2.3, the calculus of exponential generating functions. We're actually just going to be going over a quick example of using the three rules that we developed in the previous three videos. This is the example. It's a very interesting example and it introduces the Catalan numbers. Okay, so if you haven't seen the Catalan numbers, this is a really nice intro. So we will count the ways of arranging n pairs of parentheses. Each pair consisting of a left and a right parenthesis into a legal string. And so this is just, some examples are, just pairs of parentheses, things like this, right? Like this is a legal string, this is a legal string, and these are two examples that include three pairs of parentheses, okay? And we will say that we're going to say as a definition, well, let's define with each of these legal strings, we can actually associate an integer k. So we'll say we can associate an integer k with each string by finding the first two k elements that also form a legal string. So we're going to cut it in half, but so for here, let's just look at the two examples that we have written out already. The k that I would associate to this string would be 1, because after two parentheses, which is just one pair of parentheses, it's already a legal string. This is a legal string, but over here, it takes a while to get to a legal string. We have to go through 1, 2, 3, 4, 5, 6. Actually, it's the whole thing, but we have to go through 6 different elements to get to a legal string. We would cut that number in half. We would say that the integer associated to it would be 3. So this last one that I just talked about, that's something that's special. So as a definition, I mean, it looks special, right? It's like the whole thing. There's no like sub piece reading it from left to right that is a string itself. It's not a legal string, so we say a string is primitive say a string of length 2n is primitive if k is equal to n, the associated k. So meaning there is no legal substring reading it from left to right. In general, we want to know how many legal strings of 2n characters, or parentheses, have a given value k. And this is clear, there's probably more than one, right? because the way we arrange the first couple of elements, the first k elements, well, in this case, we want to make sure that that's a primitive thing, but the second piece, it can be arranged pretty much however it wants, and that's the same in every one of these. So if it has a given value k, there could be multiple different strings with the same value k. Let's go to the next page here. So suppose that Fn is the number of legal strings, of n pairs of parentheses. And this is different than the question I just asked. The question I just asked was how many legal strings are there with a given value k. I haven't mentioned any k yet. I'm just saying let Fn be the number of legal strings of n pairs of parentheses. And we'll note that if a string has a value k, then the first two k elements are definitely of a form of a primitive string. And just to maybe come up with another quick example here. So this is an example, right? The left piece, the right piece doesn't necessarily need to be primitive as it is, but the first piece is indeed going to be primitive. I'm saying that this would have a value 2, right? Because we have to go over 4 elements, so it has a value 2. Okay, well that first piece, the first 2k elements, that is going to be a primitive string. The second piece, it doesn't have to be primitive. It can do whatever it wants, as I was saying. So this gives us a way to start counting what's going on here. So I can say, here I'm going to erase this now, we can say that the string with integer k, with associated integer k, has its first 2k elements giving a primitive, and the last, well, let's see how many elements would be left. The last 2n minus 2k elements can be anything. And that means that the last 2n 2k elements, so there's legal strings. Well, they have to be legal strings at the very least, but they're just legal strings, so our function up here, f, that actually counts that. So we know that the second piece, the 2n minus 2k, there are f of nk, so there are f of n minus k ways to write the last 2n minus 2k characters. Because it indeed has to be a legal string. But then how many, and the question really comes down to how many different strings are there, primitive strings, of size 2k? And that's what we need, and we're going to need a lemma for this. Well, we don't need a lemma. I mean, this lemma will answer that question. So if k is bigger than or equal to 1, and gk is the number of primitive legal strings, then, f just as it is defined before, then gk is going to be equal to f of k minus 1. So we're going to take that on faith for now. So take that on faith. There is a proof of that in Herbert Wolf's book, but this is actually very useful, right? We can describe the number of primitive strings as the number of legal strings. And the proof actually, I mean, I can just kind of say it out loud what the sketch of the proof, how it goes is you count the number of, you consider how many there are in here, and you take an element, you consider the subset that you're counting, the set of elements you're counting, and the set of elements you're counting here, and you just show a bijection between these two sets. And it's really not that hard. It's just like adding parentheses and deleting parentheses and showing that there indeed is a bijection. Okay, but we can use this. Now that we have this lemma, we can actually use this because counting, we'll go to the next page, but counting the number of these means that there are f k minus 1 times f n minus k different strings with integer k. And so we can actually count the total number, fn, by just adding all of these together. So we're going to range over all k, and we're just going to sum all of them together. And that'll actually collect all of the legal strings in general, because everything has an associated number, so if we just count through all of those, that'll collect every single legal string. And that is really, really nice, because using this formula, you can do it. Oh, and by the way, there's an assumption that if there are just 0 parentheses, it's sort of weird to count that. We're going to say there's only one way to do that. If you start with this is a recursive formula. You can come up with a sequence. The sequence is this. The sequence we get is 1, 1, 2, 5, 14, ... This continues. If you've never seen this before, these are actually identically the Catalan numbers, which is really cool. And we're going to define them to be the Catalan numbers in a second. But we're going to say a little bit more about this. So now that the fn values are looking like they could be generated by a product of two functions, we actually kind of see that. Let's see, I grab my pointer. So right here, this is starting to look like the product, right? If this is just a sequence, and we consider the sequence here, consider fn as a sequence, then each one of these elements is starting to look like a sum, which, as we know, using the ordinary generating function, the product rule, the product rule from the ordinary generating functions, we end up getting that this looks identical to the product of two things. And in particular, we see that we get that this sequence is generated by the product of f and xf, where, and this is a capital F, right, where f is this specific generating function, where it's little f, so that's a little f, this is a big F, of k, x to the k. Okay, so if we just consider the generating function for the little f of k's, we'll call it big F, then when we multiply f times xf, we actually end up getting all of these sums as we desire, and that's just using the product rule that we developed in the ordinary generating function. And you should look back at that to see if that does indeed match up, and it will. And let's go to the here. I'll put a period here. So let's go to the next page here. So the original occurrence that we were given was that, let me see. So it was the recurrence that we were given was that f n, or sorry, that's supposed to be a little f, or yeah, little f of n is going to be equal to summing up all of these little f. So this is what we had before. And now what we're saying is we know more about the right-hand side, we know more about the left-hand side. We can actually we can start using the generating functions. We can go from this recurrence and move to a generating function, because the left-hand side, if we multiply by x to the n, add them all together, we end up with our big F of x. But notice that the big F of x does not account for when n is equal to 0, so we're gonna have to subtract off a 1. Okay, and then another thing is that the right-hand side, well, I said it was the product of x and f of x, and then, or of xf and f, right? So I'm going to write that as x f of x squared. Okay, and it's just multiplying f times fx. Okay, so it's just two f's and a single x. So that's what you end up getting. So this turns into this using the generating functions. And so we can just, from this, we can just simply solve for f of x. Maybe it's not as simple as you might think, because before we were just given some linear expression. It was a lot easier because it was linear. This is a quadratic. Once we solve for x, or f of x, we do end up getting that we get a couple options, really. It's 1 plus or minus the square root of 1 minus 4x all over 2x. And when I say a couple, I literally mean 2. There are two options here, a plus or a minus. And we need to determine which one is going to give us what we need. Well, we have requirements, right? We have something that we need to meet. If we just think about this for a second, if we choose the minus, so let's first try the plus. If we try the plus, then what's going to happen? If I choose f of x to equal 1 plus the square root of 1 minus 4x all over 2x. Well, what do we want? We really want, when we plug in 0 into this function, we really want 1 to come out. But if I plug 0 into this function as is, well, what happens? If I plug 0 in, the denominator, well, that's just 0. I mean, so we're hoping for something else to happen in the numerator here. But if this is 0, we kind of want this to be 0, but it's not. It ends up being 1 plus 1 minus 0, so 1 plus 1. So it's a 2 over a 0. So this thing blows up. It goes to infinity, right? When we plug in 0, this is not what we want. So f of 0, in some sense, equals infinity, and we don't really, that's not what we want. We want it to be equal to 1. So f of x is actually going to be equal to this, because now when we put in 0, or we take the limit as it goes to 0, you'll see the limit as x goes to 0 of 1 minus the square root of 1 minus 4x over 2x. Once you use L'Hopital's rule, it's very straightforward. You end up getting that this is actually indeed going to be equal to 1. Okay, so then we get that f of 0 is indeed equal to 1 here. And that is really, really great. Okay, and why is this great? So we have this function right here. I guess I'll outline it. this function right here, this is the generating function for the Catalan numbers, okay? So we'll write that. This is the, and this, remember, is an ordinary generating function for the Catalan numbers. And these numbers now, if I just go back one page, these numbers are the Catalan numbers. This is the sequence, and it's very useful, okay? So I hope you guys got something out of this video, and thank you for listening.